We've introduced the Hermite polynomials, which are just boring polynomials, and we've also introduced the Bessel functions, which are much more interesting because they have a series expansion which does not terminate. Now, there's main difference between the two. If you look at their generating function, which really is the feature in the generating function that can explain that difference. So pause the video and try to think about this. Let's first focus our attention on the case of the Bessel function. So for Bessel, we have a generating function which we can write as the product of two exponentials as follows. So we have exponential x over 2t times exponential and then minus x over 2t. So just focusing on the essential part here, if we write this as a series expansion, so we have a sum over r and then something like t to the power of r for our first factor and some prefactors which we don't care about. And then for the second factor, we have a sum over s. And then we have 1 over t to the power of s. Okay. So now that we have this, we need to collect all of the like powers of t. So for that, we're going to use a substitution. N is equal to r minus s because we have the 1 over t here. So we can also write this as s is then equal to r minus n. Or we can also represent that graphically. Just a quick recap of what we did earlier by having this diagram where each of the crosses here corresponds to a term in the product of the series expansions. So if this is r and this is s, we can see where we have certain values of n. So for example, you will see that if you have n is equal to 0, this will happen when r and s are the same. And then when we have r is equal to 1 and s is equal to 0, then you can see here that this is happening for n equal to 1, and here we have n equal to minus 1. The important part here is because these lines are oriented in that direction, is that for a given line, if we're on a certain line and we look at all the possible values that r can take, you will see that r can basically start at 0 and then run all the way towards infinity here. So this is why the series expansion does not terminate. If we now contrast that to the Hermite polynomial and its generating function. So again, the Hermite polynomial has a generating function which can be written as a product of two exponentials, but in this case the exponentials are exponential minus t squared and exponential 2tx. So if we again expand that as a series expansion, we have some prefactors which now we're not interested in. Then we have t to the power of 2r, and then for the second summation it's s, and then t to the power of s. Now in this case, when we want to collect like powers of t, as for example t to the power of n, then we need to make the substitution n is equal to 2r plus s. Or if we write s as a function of n, we have then s as a function of r, rather, we have s is equal to minus 2r plus n. And this is a fundamental difference here because now we have minus 2 as coefficient here, whereas previously we had a positive coefficient. Now the fact that this coefficient now becomes negative means that the orientation of these lines will flip. And that will have profound differences, as we can easily see here when we make that diagram. So again, for the details, please refer to the videos dealing specifically with that. So if we have here r and there s, in these videos we've seen that the different values are, for example, oriented like this and like that. And then we have one over here and then one over there. But the important part is that now, since they're oriented in that direction, if we look at a single line here, any line will only cross a finite number of points here. And this means that the series expansion will terminate and that we will have a boring polynomial. So the fundamental reason is this change in sign here, this change in orientation of the line. And that then boils down to the fact that if we look at the series expansion here, we have 2 times positive exponents of t here. So this is a situation where we don't have a singularity in either of the terms of our generating function, which is different in the case of Bessel functions, because there we have a factor which does not have a singularity and a factor which does have a singularity. And that causes the series expansion not to terminate for the case of Bessel functions.